Okay, before we look at the data, let's review the procedure. The first thing we need to do is we'll make a standard calcium chloride solution. Note that we're starting with calcium carbonate. The reason we do that is that calcium chloride tends to be hygroscopic. That means it absorbs water from the air. And so it's very hard to weigh out accurately and know exactly how many moles you have. But we can measure calcium carbonate very accurately, and then we'll add a little hydrochloric acid and turn it into the calcium chloride that we want. So you'll be given the number of grams of calcium carbonate that we start with, and we'll transfer it all into a volumetric flask. I've got a picture of a volumetric flask right here beside. Note that it's very, very accurate. If we fill it with water to this line, we'll have, in this case, this is 100 milliliters, so you'll have exactly 100 milliliters. But it's a very precise piece of glassware. Okay, and we'll mix it together, and that will be our standard calcium chloride solution. We will know the molarity of the calcium chloride in this flask. Then we'll need to prepare our burette. We'll rinse the burette with distilled water, and then to make sure it's clean, and then we'll rinse it with EDTA to remove all the water and make sure that all of the water, all of the liquid in there has the same concentration, and it's all that EDTA. We'll fill it with the solution, make sure we remove all the bubbles. We'll need to be sure that we're reading the burette correctly. We've talked about this, I think, in the very first session, so I'm glad we had that opportunity to look at burettes. But burettes are upside down. If they're completely full, they'll have 0 milliliters. And that's because they are calibrated to deliver. So when they're full and they haven't delivered anything yet, it's 0. And when they're nearly empty and they've delivered all 50 milliliters, it'll read 50 milliliters. Okay, so you'll see in my little section that I've got over here that the 19 is above the 20, and that's just the reverse of what you would find on like a graduated cylinder. You want to read at the bottom of this meniscus, and these marks are milliliters, which means that these littler marks are 1/10 of a milliliter. And we need to read between the lines, and so we'll be reading to 100th of a milliliter. All of the measurements given to you that are from a burette will have, we'll be reading all the way to the hundredths. Now this one is going to be 19. Each one of these lines is 0.1, so this is 19.7 to this line here. It looks to me like it's pretty much on that line, so I would say 19.70. There's an excellent video on how to read a burette on the website. All right, so we've got the burette full of EDTA. We need to titrate the calcium chloride solution. So first, all of our glassware needs to be rinsed with distilled water. Distilled water doesn't have any calcium in it because we're going to be measuring calcium. If you rinse stuff with tap water, then you're adding what we're measuring. So you can't do that. You have to make sure everything's rinsed with distilled water. We'll transfer 50 milliliters of the calcium chloride solution to an Erlenmeyer flask. We'll add some ammonium chloride buffer. That's just to keep the pH in the right range so that we'll be able to see the reaction and the ectochrome black indicator will work. Okay, read the level of the EDTA in the burette. And then we add the EDTA to our solution very, very slowly. Now initially, the solution will have this red color that indicates that there's free calcium in the solution. As we add EDTA, the calcium will get bound up. It's no longer free. And when the concentration of the EDTA, or I'm sorry, the number of moles of EDTA is equal to the number of moles of calcium, we'll get this nice blue color. It's very important that you do this slowly so that you get those two numbers to match up exactly. Okay, now from this data you should be able to calculate your EDTA concentration. Then we'll repeat the whole procedure, but this time instead of using our standard calcium chloride solution, we use tap water. And if we add tap water,